Hi, regular and honors chemistry students. If you missed class this morning on Zoom, you should be watching this video to catch up, to be on the same track as your classmates. So we were looking at the polarity of molecules this morning, and this is a continuation of Thursday's video lesson. In that lesson, I mentioned the difference between polar bonds and polar molecules. And so we're really focusing our attention on whether or not the entire molecule is polar on the whole, and there's several important points about that. You need to have at least one polar bond in the molecule for it to be polar. If you don't have any polar bonds at all, it's not going to be possible to have a polar molecule. However, even if you have polar bonds, there are some molecules where polar bonds cancel out, and that's when you have them pulling in opposite directions. So in a linear molecule like carbon dioxide, those two polar bonds cancel out and you get no net dipole moment. However, if you have something like a bent molecule, like in the water molecule, those dipole moments don't cancel, they add. So you need to see whether or not you've got polar bonds in the first place, and then how are those polar bonds arranged, because they might cancel out. So let's apply that to some more complicated looking molecules that aren't just linear or bent. So to summarize from that other video on here, we've already answered some of these. This is a non-polar molecule because there aren't any polar bonds at all. So if you don't have any polar bonds, it's going to be a non-polar molecule. Alrighty. In contrast, the HF molecule, it has one bond total, and that one bond, which is polar, right? There's a dipole moment pointing towards the more electronegative fluorine atom, partial negative here, partial positive here, so you have a polar molecule. Now I just mentioned water and carbon dioxide. This one's polar, in part because it's bent with two polar bonds that add up. They're both kind of pointing upward the way that I drew it here, okay? On its side, right, it would be, these two dipole moments would sort of add up this direction. Okay, so the water molecule is polar, super important polar molecule, whereas carbon dioxide is nonpolar. It's linear, and the two polar bonds, or the two dipole moments, cancel. All right, so there's some that I asked you to do for homework, and those were 9, 10, and 12. So let's talk about those quickly. This is a bent molecule just like the water molecule. You need to start off with the Lewis structure, apply VSEPR, figure out what the shape is. The shape is tetrahedral parent geometry. Okay, tetrahedral parent geometry, because we've got 4 effective pairs of electrons around that central atom in here. And so those 4 effective pairs of electrons are going to give rise to tetrahedral parent geometry. But with 2 lone pairs, we've got a bent molecule, just like the water molecule. Okay, so this is bent shape. And so are those dipole moments going to cancel out between all these bonds here? And first of all, they are polar bonds, sorry. They are polar because sulfur and hydrogen do not have the same electronegativity. Sulfur's more electronegative, and so these bonds are polar with dipole moments pointing in towards the sulfur. And they don't add up. They don't cancel out. They do add up to give you a net dipole moment. So this is a polar molecule. Diatomic iodine, That's two atoms of iodine bonded together. There's the Lewis structure, but we don't need to draw it to know that that's going to be a nonpolar bond. So there's no polar bonds at all. So this is a nonpolar molecule. And the same thing can be said about oxygen. Even though it's a double bond, once you get your final Lewis structure, it doesn't matter if it's a triple bond or a double bond or a single bond. What matters is that it's a nonpolar bond. So the molecule is nonpolar. You need at least one polar bond to get a polar molecule. Now, the more complicated ones that we covered in class today. Start with this one. The structure of CH4 we saw the other day is tetrahedral. It's a tetrahedral shaped molecule. Okay? So, if you have a tetrahedron, the tetrahedral shape looks like this. It's when you get 4 balloons, right? And you tie those 4 balloons together, right? If you were here for the lab, you get something, that actually looks pretty terrible. Let me try it again. I can do better even though I'm drawing balloons, right? Boom, boom. Something like that. Tetrahedral shape. Now, here we're talking about carbon bonded to 4 hydrogen atoms. Each one of these bonds is actually a polar covalent bond. Carbon and hydrogen do not have the same electronegativities. Carbon's is 2.5 and hydrogen's is 2.1. So carbon, being the more electronegative atom, is going to draw those bonding electrons toward itself. Okay, so the electrons are being drawn in toward that carbon. Okay, I'm trying to draw those dipole moments three-dimensional as best I can. Now, what's the result here? It turns out, it's hard to visualize this type of thing, but it turns out this is kind of like a tug of war in 3 dimensions with carbon in a battle against all these hydrogens. And carbon is pulling in the electrons all around it, and they're spaced out evenly around the carbon atom. And so it turns out when you add up all of these vectors, dipole moments are types of vectors which have a magnitude and a direction. It turns out what you end up with is no net dipole moment. They cancel out. Like in the carbon dioxide molecule. In the carbon dioxide molecule, they canceled out, and it's easy to visualize that because it's like the tug of war we're familiar with. Going to the left and going to the right, equal and opposite, cancel out. Here you got to trust me. When you have a molecule like methane with 4 equally spaced out equivalent dipole moments, same magnitude, just these different directions, they also cancel out. Okay? Basically, if you imagine some type of boulder floating around in space with 4 spacemen around the boulder and they're all pushing in on the boulder won't move. They all cancel one another out. Okay, so in the methane molecule, there's no net dipole moment. And like I said, that's hard to visualize, but you got to trust me on that one. Okay, so even though there are 4 polar bonds, they cancel out. There is no net dipole moment. And as a result, what type of molecule? You got it. Non-polar. I kind of ran out of room writing that in there. Okay. Now, the last one to consider for today. Let's see here. Actually, there was 2 other ones. I introduced one that's not on this page, so I will talk about 2 more. Let's do this one though, ammonia. Okay, so ammonia, we drew its Lewis structure the other day, and we figured out that ammonia is trigonal pyramidal. Around the central atom, 4 effective pairs of electrons. So here the parent geometry is actually the same type of parent geometry. It's tetrahedral parent geometry. But instead of 4 bonds, we've got a lone pair with 3 bonds. Okay? So in the middle, we've got the nitrogen atom, lone pair up top, and then these 3 bonds down to the hydrogens. Now, if you compare that structure with the methane one, they're very similar. They're both arising out of tetrahedral parent geometry, but whereas this one has atoms connected everywhere, this one has a lone pair. Okay, so there's not a bond to another atom up here. It's just atoms down in here. And so we have 3 bonds. Now these bonds are polar bonds. If you go back and you look at the electronegativities, right, you can see that nitrogen and hydrogen don't have the same electronegativity. Nitrogen is 3, hydrogen is 2. So nitrogen's more electronegative, and it's going to draw in these bonding electrons toward itself. Like we saw up here on the methane, same type of thing, but with an important difference. We don't have that 4th bond downward. It's not there. Okay? It's a lone pair of electrons. And so what that means is we have a little bit of asymmetry. Asymmetry means like it's not symmetrical. It's not perfectly balanced out in all directions, okay? And when you have any element of asymmetry, you're not going to have your dipole moments canceling out. They're going to add up. They're all kind of pointing upward without a counterbalance of something downward. So we do have a partial negative end of the molecule and a partial positive end of the molecule. So, given that this is a different shape, even though it's arising out of tetrahedral parent geometry, we can say we have 3 polar bonds which add up. Once we've considered the shape, you have to consider the shape, we can recognize that in a trigonal pyramidal shape, that's what this is called, there's a little bit of asymmetry, right? You don't have that bonding atom up top like we did in methane. And so because of that, those 3 dipole moments add up. So what's the molecule? Polar. All right, the final example I gave the class today was an exception to the octet rule, but it's an important one to know about, at least in the context of this discussion, polarity. So it's an exception to the octet rule, so I would never ask you to draw the Lewis structure. But given that this is the Lewis structure, what would be the shape of the molecule and would it be polar or not? Okay, so by the way, it's an exception to the octet rule because boron only has 6 valence electrons around it, and that's not 8. And yet this is a fairly stable molecule. It exists anyway. So, okay, so what's the shape? We have 3 effective pairs of electrons repelling one another. So we know that the parent geometry is trigonal planar. Trigonal planar parent geometry. And since all 3 of those effective pairs are bonds, the molecule itself is trigonal planar. Central atom bonded to 3 other atoms. Now these are all boron-fluorine bonds, spread out equally, very symmetrical. And so it turns out that these polar bonds, fluorine is more electronegative, so it draws the electrons toward itself. Partial negative here, partial negative here, partial negative here, and basically 3 partial, positives on the boron. Is there a side of this molecule that is partially positive and the other side's partially negative? No. These polar bonds, which are the dipole moments, which are vectors, they cancel out. One up, one down this way, one down that way, and they're all equal. They cancel out. All the dipole moments cancel out. So these 3 dipole moments cancel out. So there is no net dipole moment. Again, you've got something that's very symmetrical, right? Trigonal planar parent geometry. If I could have drawn it perfectly, I would have. I just can't. So you got to imagine the ideal trigonal planar shape spread out perfectly, looking very symmetrical. 120 degrees all around each bond angle, okay? And they're the same types of bonds, and even though they're polar, because of how they're pointing, they cancel out. So we have a non-polar molecule. All right, that about sums it up what we covered today. Please let me know if you have any questions. Bye.